The equilibrium constant is central to almost everything in the molecular life sciences. As its name implies, it is a constant for a given reaction as long as that reaction is at equilibrium. It equals the product of the equilibrium activities of the products, each raised to the power of its stoichiometric coefficient, divided by the product of the equilibrium activities of the reactants, each raised to the power of its stoichiometric coefficient. While the value of K depends on the particular reaction and the temperature, it is independent of the total pressure or concentration of the reactants and products. The activity of a substance is related to its partial pressure or concentration. But as we'll see when we learn about the relationship between equilibrium constants and free energy, equilibrium constants and therefore activities need to be unitless. So to eliminate the units, the activity of a gas is set equal to its partial pressure in bars divided by a reference partial pressure of 1 bar, while the activity of a solute is set equal to its molar concentration divided by a reference concentration of 1 molar. For pure solids and pure or nearly pure liquids, including solvents, we simply set the activity equal to a unitless value of 1. We can do this because the effective concentration of a pure liquid or solid does not change as the reaction proceeds. So let's look at a particular reaction, specifically the reaction of carbon dioxide with ammonia to form urea and water. This is a heterogeneous reaction since it involves more than one phase. The carbon dioxide and ammonia are gases, the urea is a solute, and the water is a liquid. According to the law of mass action, the equilibrium constant for this reaction is the activity of urea times the activity of water divided by the activity of carbon dioxide times the activity of ammonia squared. Using the rules for activity, we can expand this expression as shown here. Since urea is a solute, we replace the activity of urea with the concentration of urea divided by the reference concentration. Since water is a liquid, we replace the activity of water with 1. And since carbon dioxide and ammonia are both gases, we replace their activities with their partial pressures divided by the reference partial pressure. But to save time and avoid writer's cramp, we usually don't show the reference concentrations and partial pressures, and we almost never show this unitless 1. So the expression simplifies to the concentration of urea divided by the partial pressure of carbon dioxide times the partial pressure of ammonia squared. You might think this expression looks objectionable since it seems as though we're combining partial pressures and molar concentrations in a single expression, which seems like it should be illegal. But remember, this is really shorthand for this. And so the units all cancel out, giving us a unitless equilibrium constant.